For the final example, I'm going to cover that on Friday, but here's basically, I think I may give you, based on what we cover, I'll give you some formulas. There are some things that are going to get a little, I'm not going to give you, if I give you a problem on student T distribution, I'll give you the functional form and the table. I'll give you the value for the table for K and Q, the confidence interval. I'll give you things like that. I'm not going to give you base theorem. I'm not going to give you, for instance, information about, remember that link problem? That I'm assuming you understand. But I will tell you, and for the Gaussian stuff, I'll put up the Gaussian distribution on the board if you want it and stuff like that. And central moments, if it's Gaussian, it's going to be 1 times 3 times, and then it's really n minus 1 times sigma to the nth power. I'll give you some information like that, but I'm not going to just give you a ton of everything. The variance of, and this is going to be the variance of the sample. So if you have 1,000 in a population, you sample 20, then this is the standard deviation that is a random variable of the 20 you sample. It'll be a mean squared value of standard deviation. This has the form of u to the fourth minus sigma to the fourth, and then it's times n over n minus 1 squared. Now you can see as n gets very large, and this is the sample size, that becomes n over n squared, or 1 over n. And then it starts looking like u to the fourth minus sigma to the fourth over n. And that would be a biased value of the variance. The variance of the variance. This is exercise 4-3.1.
For the random waveform of figure 4-1, find the sample size that would be required to estimate the true variance of the waveform. Part A is a variance of 1% of the true variance if an unbiased estimator is used.
All right, so variance, all right, hold on, of the true variance. I mean, what's the variance of the variance? Of sigma squared, of the actual variance, the true variance. This value here, the variance of the sample size, and this is the unbiased, is going to be 1%, 0.01 times the true, and he says variance, right? Variance is sigma squared, that's the actual value. Now, he says, we'll get to the waveform in 4-1, but I'll put this up there. For all this stuff, the waveform in figure 4-1 has it's Gaussian, by the way. It has a sigma squared value of 9, and it has a mean value of 10. So it's going to be u to the fourth minus sigma to the fourth, and now it's going to be n minus 1 squared. You're going to find out when n's large, you can basically use just 1 over n. What we have to do is, if this is Gaussian, we're going to go back to the waveform. If it's Gaussian, this here, sigma to the fourth, is actually sigma squared squared. U to the fourth, because it is the fourth center moment, is 1 times 3, and then it's going to be times sigma to the fourth. This is really just 3 times sigma to the fourth, right?
Because that's sigma, that is the Gaussian sigma.
That's the actual value of sigma squared squared. So that is of the variable that is Gaussian. Take the variance and then square it. So it's of the waveform up there. Sigma squared over 100 here is equal to, and look, u to the fourth is 3 sigma to the fourth, minus sigma to the fourth is 2 sigma to the fourth, back to the waveform at 4-1, and that's times n over n minus 1 squared. Really, at this point, it's just a matter of being careful. We know what sigma is, all right, sigma squared. So I'm going to get rid of one of these sigma squareds. So if I invert it, I have 100 equals n minus 1 squared over, and it's going to be 2 sigma squared n, and now it's straightforward at this point. What I'm going to do is multiply both sides by 2 sigma squared n, so I get 200. And that's going to be sigma squared n is equal to n squared minus 2n plus 1. We're just solving for the roots here. And there'll be 2 of them. Now, sigma squared is 9. So now I have 9. So this is really 1800. This is the unbiased, by the way, not biased. 1800 n is equal to n squared minus 2n plus 1. Or I have 0 equals n squared minus, and this is going to be 1802n plus 1, and I believe on this one n is equal to 1802. The unbiased one. All right, now for the biased one, let me just put this is going to be biased. The variance of S Now this is just s squared, and that's going to be equal to u to the fourth minus sigma to the fourth, but down here is just n, right? No, this is biased. This is biased.
Well, yeah,
So it doesn't matter the symbols. This is unbiased. I'll give this to you. Unbiased is equation. That's equation 4-11. Take a look. Why would you use biased if unbiased is the more proper way to get it? Because that's going to give you true values related to the entirety of the sample. Of the population. So for this one, what do you get for this? Over here, the only thing that happens is what? This is 1 over n, so n comes up here, right? Oh, sorry. Got that wrong. Over n, right? So n is going to be equal to 100 times 2 times 9. That's 1,800, isn't it? All right, by the way, he says this is only good for a large sample size. It means you're assuming that you take a fair number of samples. 4-3.1, I think he has 10 values, and he asks for the mean and the standard deviation of them. But that's just summing all the numbers, getting the mean, and then getting the standard deviation by getting the squared value, actual x squared of that, and then take x squared bar minus x bar squared, and you get the standard deviation. 4-3.2.
a zero mean Gaussian random time function is sampled so as to obtain independent sample values. How many sample values are required to obtain an unbiased estimate of the variance of the time function with a standard deviation?
Oh, hold up. Variance of the variance, obviously, right? And this is going to be square root because it's the standard deviation. Just read that slowly again, the last part.
How many sample values are required to obtain an unbiased estimate of the variance of the time function with a standard deviation that is 2% of the true variance?
Standard deviation, square root of the variance, right? That's the variance of the variance. It's going to be 2%, 0.02 of...
True variance.
Okay, so that's sigma squared. Standard deviation, square root of the variance. It's unbiased. Now I'll square it. So now I get variance of s tilde squared is equal to, and it's u to the fourth. Remember, that's a Gaussian, sigma to the fourth, and then you're going to have the n over n minus 1 quantity squared. So we have this, and we've got to square it. So it's going to be 0.02 sigma squared. That equals u to the fourth minus sigma to the fourth times n over n minus 1. Now, as long as we understand what u to the fourth is and stuff, you got no problem. This one is Gaussian. So what is u to the fourth, anyone? That's going to be 1 times 3 times, it would be 5 if it was a higher order moment. This is a central moment, right? It's Gaussian. It's going to be 1 times 3 times sigma to the fourth. I've got that. So I put in 3 times sigma to the fourth minus sigma to the fourth. So I have 3 sigma to the fourth minus sigma to the fourth over n minus 1 squared is equal to, now this is going to be 0.02 squared sigma to the fourth. It's obvious the sigma to the fourth so you can get rid of it. So for this one, I flip it. When I flip it, I get 1 over 0.02 squared equal to n squared minus 2n plus 1, and then downstairs I'm going to get 2n. So when I multiply over here by 2n, I get this, and then you can see obviously what happens here. I'm going to have 0 equal to n squared minus, and it's going to be 2 plus 2 over 0.02 squared and plus 1, and that means n equals 5,002. Now they suggest in some of these places to plot the function. Like, call this, if you're wondering, and I'm just saying this for reference, in case you've got a question where you get 2 values, suppose you had f of n equals this. Now, if you look at f of n, I'm not sure what it looks like versus n. It may do this kind of thing. This one would be negative. This is the one you want. It's the root that sets it equal to 0, and it's always going to be on the positive side of the value. But sometimes it's possible to get a curve like that too, where you're going to get positive 0, and you had that for 0.04 or something like that?
Yeah.
You can get something like that, and the only way you can know which one to get is you have to look at the statement of the problem. If it requires a large number of samples, it has to be the larger one. Suppose I say I want the standard deviation of the variance, in other words this, of the unbiased variance, equal to be 10. What changes? That's it. Just replace that by 10 and square it, you get 100. Put 100, put it over here, and solve. That's it. If it is Not a Gaussian if it is like constant value, uniform distribution. That's where you get that delta x, the spread over squared over 12. That would be the variance for a uniform distribution over a range delta x. So it wouldn't be just 1 times 3 sigma to the 4th. Okay.
It is desired to estimate the variance of a random phase angle that is uniformly distributed over a range of 2 pi.
All right, I'm going to say this. In this book, he goes from minus pi to pi. Now, you don't have to do that. You can go from 0 to 2 pi. It won't matter. This is the delta x in the equation. If this is uniform, this is 1 over 2 pi. So if it's uniform, you're going to find that he'll have the standard deviation is going to be delta x squared over 12. We could do that. If we have this, what's the mean value of this? Is 0. Now, I put it that way. The problem statement says from 0 to 2 pi. But anytime you have a phase angle that's uniformly distributed, you can take this region, you can move it up here, you can go from 0 to 2 pi, or from minus pi to pi. As long as the range is pi, you cover the entirety of the spectrum possible for phase angle. Now, we could do it the other way, but you know why we do it that way? The mean of that's 0. So if you wanted to calculate, this is the phase angle theta, call this f of theta here. And now suppose I want so the mean value of theta is equal to 0. So how do I get sigma squared of theta? Well, what's the definition? You would take the value of the variable, theta, minus the mean 0, right? So it's theta squared, right? Then you have to take the probability density function times that 1 over 2 pi, and then you integrate that d theta. From minus pi to pi, couldn't you just integrate 2 times from 0 to pi? So 2 from 0 to pi, now you're going to get 1 over pi, and then you get theta cubed over 3, evaluated from 0 to pi, and that is equal to 1 over 3 pi, and that's going to be pi cubed should be pi squared over 3. And that is sigma of theta squared. Let's see what this turns out to. Delta x is 2 pi, so if we have 2 pi squared over 12, that's 4 pi squared over 12 is pi squared over 3. They're the same. Remember, it's uniform. Don't trip up and use Gaussian's assumptions there, because what do we do with Gaussian? If it's Gaussian, the variance of s to the squared is equal to u to the 4th minus sigma to the 4th n over n minus 1 squared. But here, u to the 4th would be just 3 times sigma to the 4th. It's not. What did he say about this statement? Read that part again.
Find the number of independent samples that are required to estimate this variance with a standard deviation that is 5% of the true variance.
Okay. So now,
With the standard
this
deviation.
variance, this standard deviation. So we're going to have to square this. So it's 5%, so it's 0.05 sigma squared. The standard deviation would be the square root of this, meaning the actual variance of the variance. And that's u to the 4th, which is, if we wanted the 4th central moment, how do we get it? Start with the probability density function. You've got to do this just by definition. So you take the probability density function's values, 1 over 2 pi, and it's uniform, and I'll take that outside the integral. Then we integrate, right? Technically, it's from minus pi to pi. That's the range I put. You can go from 0 to 2 pi. The only reason I didn't do that is the mean would not be 0. That's the reason I chose minus pi to pi. And now you're going to put down the value of the function. Well, that's theta minus 0. You'll notice there's no minus some value. Theta to the 4th d theta. I can go from minus pi to pi, or, because it's an even function, just from 0 to pi multiply by 2, and I choose to do that. So now I have u to the 4th equals 1 over pi. And then I integrate that, I get theta to the 5th over 5. So now when you have that, you get 1/5, and then you have theta to the 5th, which is pi, so it's pi to the 5th. And that means this is going to be pi to the 4th over 5 is going to be u to the 4th. I have pi to the 4th over 5 minus, and this is going to be what? Pi squared over 3 squared. Then I have n over n minus 1 squared. But here, I'm going to put in, this is pi squared over 3. I'm going to go ahead and multiply that out. So here, I get 0.05 over 3 squared times pi to the 4th is equal to, and here, I'll take pi to the 4th outside, and I get 1/5 minus 1/9 here. Then I have the n over n n minus 1 squared. I'm just doing this to get rid of the pi's. Yeah, we're looking for n. And just for the record, I'm going to ask unbiased. I'm not going to ask biased. Now, I'm going to can I get rid of pi to the fourth, everyone? Pi squared over 3 is sigma squared, right?
Oh, okay.
And I have to square that because it's sigma to the fourth, right? But I got 1/5 minus 1/9, common denominator 45, right? So I have 9 minus 5 over 45, 4 over 45. You give me that, guys? So then I'll multiply both sides by 45 over 4. So now when I flip it, I get 3 over 0.05. This is squared times 4 over 45. And that's equal to n squared minus 2n plus 1. And on this side, here I multiply by n. I'm just rearranging this. Now I'm going to put everything equal to 0. You tell me what you get. So here I'm going to have 0 is equal to n squared minus 2 plus 4 over 45. And then it's going to be 3 over 0.05. All that is squared. And it's going to be plus 1. And what do you get for n? Well, 322. You can put in f of n here and then graph it too, just to see where the zeros are. 4-3.4. F of x is what? E to the minus x greater than or equal to 0, and 0 else.
Independent samples are taken from a random time function having a probability density function of each. How many samples are required to estimate the variance of this time function with a standard deviation that is 5% of the true variance?
Okay.
True value of an unbiased estimate.
Yeah, always unbiased. So the square root of that is standard deviation. This is the standard deviation. And he says, what percent?
5%.
0.05 of the actual standard deviation, right? We're going to use this formula, and this is going to be u to the fourth minus sigma to the fourth times n over n minus 1 squared. And by the way, if n gets over 1,000 and stuff, it's basically just 1 over n. What do I need next?
So you could get the mean value of
Let's do
the
it.
function.
How do you get the mean value?
You do the integral from
0 to what?
infinity. X times e to the negative x dx.
Which is 1.
You
Now
need
what?
that x squared value. You need squared
How do we
value.
get the x squared
Do it again.
mean?
X squared.
I'm going to go from 0 to infinity of what?
X squared
Shocking.
e to the negative x dx.
This is 2. Now, what else do we need, Nick?
Wait, we need sigma first.
Sigma squared is what? It's this, right? 2
Wait, no,
minus 1 squared, which is 1, isn't it? Now, what do we need, Nick?
Let's work central moment.
How do we get that?
1 times 3 times sigma to the fourth.
Wrong. Nick, back to this. What are we going to go from? Integrate from 0 to infinity. What do we put in here? X minus x bar squared.
That's what I was,
No,
yeah, that's
4.
the one I was going
4.
for. Yeah.
4. Right? 4 central moments.
That's what I was going
Times, that's what I'm working on, Jack. E to the minus, you know what? Be thankful for your calculators. dx, correct? What is x bar?
Is
1.
1.
Tell me what it is. 9? All right. Now I'm going to take this and square it. And that's going to be u to the fourth minus sigma to the fourth over n minus 1 squared. So we've got that is, where is it? 0.05 sigma squared. So I have to take 0.05 squared sigma to the fourth equals, and we got u to the fourth is 9, right? Minus sigma to the fourth. Sigma squared is 1. And then it's going to be n over n minus 1. Let's see what you guys get for this. Sigma squared is 1, so this is 1. I'm going to replace this by 8. Now I flip it and I get 8 over 0.05 squared is equal to n squared minus 2n plus 1 times n on this side, so 0 is equal to n squared minus 2 plus 8 over 0.05 squared plus 1. What do you get for n? What I'm going to do now is just put up PowerPoints on the student T and what's called the confidence interval. Now they're talking about something that ultimately has to do, what level of confidence do you have in the statement you made about 90% or 95% of the possible values of the mean or standard deviation are within a certain range. And first he brings you back to, well, if we're talking about just the variance of the mean, This isn't the variance of the variance. If it's a large set of samples, then it's just sigma squared over n. Otherwise, you have to do that n over n minus 1 squared business. But for a large set, and this is out of the book, true mean of 10, that's 4-1, that waveform in figure 4-1. So how many samples do you need? You can see this as how many samples do you need to estimate the variance of the mean within 2% of its true value. There's the variance of the mean. The true mean is 10, 2%. So this value has to be squared. Now you can find out you're going to have that sigma squared is 9. So you get n basically equal to or greater than 225. That's the straightforward one in section 4-2. There's nothing new here. Now suppose n is 225 and we compute a sample mean. Are we guaranteed that our value is within 2% of the true mean? This is the statement that's important. We're not. Now, the assumption is this. If we have a variance of the sample mean, right, and we have this many samples, we can use that, and we know what the variance of the variance is, and here's something that should make sense. So the actual variance, sigma squared over the variance of the mean. Now remember, he's talking about the mean, not the variance of the variance. Sigma squared over n, so it's 0.04. We want to know the probability that we're actually within 2% of the true mean. Here's a statement I don't like. We have to know the true mean. If we know the true mean, why are we getting a sample? And the reason is because later, as we get into this, you'll see how we actually estimate this stuff, including the sample. Okay, so how do you do it? Well, we see the variance is 0.04. Right? Now, remember how when you did this, you really took the value like x minus x bar over sigma. What we're talking about now is using this value of the variance of the sample mean like we would value of the true variance. What we're going to do is take this value, we got to take the square root of it. So what's down here is going to be, he wants to know if you're within 2% of the sample mean. Now sample mean is 10, right? So you could be lower than that. That would be 9.8. It would be 10 minus 10.2, right? That would be the lower value. The upper value would be, so he wants, if this is the actual mean value, we know, we're assuming it's Gaussian, this distribution here is going to be a PDF with a probability density function of 1 over square root of 2 pi, and here it's going to be the actual sigma, unbiased sigma there, unbiased standard deviation, square root of the variance. Then it's going to be EXP, and here it's going to be minus the quantity x minus x bar squared over 2, and here it's s tilde squared. You're not going to use the actual sigma, now you're using the variance that you calculate. If we want to be within 2%, x here is 10. The lower value would be 10 minus 9.8 because 2% is 0.2. If you're within 10% of this, that's 2% lower, 2% higher. Or this is going to be 10 minus 0.2. This is 10 plus 0.2. But these values, what happens is when we actually look at the probability of this happening, so the probability of being from, and here would be 9.8 greater than or equal to x, and that's that random variable, less than or equal to 10.2. The way you have to get this is you're going to get that variable, I think he calls it z, is going to be equal to the actual value of x, the x or not, minus the true mean over, and now it's, for this particular one, it's just going to be s here. So that's, he has s tilde squared is equal to 0.04. So s tilde is equal to 0.2. If you look at the values of this is in chapter 2, where we actually used the table. He had tables to reference, but remember those Q functions and the phi function thing? So this is going to be equal to phi function of, and now it's going to be 9.8 over, should be x minus x bar over the square root of s squared, s tilde squared, minus phi of x bar plus x, plus, this is actually going to be x bar plus 0.2. This is x bar minus 0.2 over 0.4, because this is, 0.2 here. Now, what actually they'll show you in there, the only thing we're doing is getting this area, is what I'm trying to say, from this function. You remember doing this kind of stuff, guys? This is chapter 2. That's what he's showing you here. This is f of 10.2 is basically, when you go ahead and take care of the normalization, you take 10.2 minus 10 is 0.2, over 0.2 is 1. You're going to have 9.8 minus 10 right there, which is going to be equal to, divided by 0.2 is minus 1. So you get this. Remember, that's that phi function that integrates from a point to infinity. So you're basically taking 2 times, this itself is equal to 2 times phi of 1 minus 1, and he gets that. But the whole idea, if you understand that this is the density function for the mean, because remember, when we did this, we got the variance of the sample. That's the idea. And it's less than sigma squared. It's that divided by n. When you do that, that's 0.04. The square root of that would be the standard deviation of the sample mean. And remember, when you're talking about mean, the whole idea is this: the more samples, the smaller the variance gets. You can see that happening. So that would be the value. Think about that distribution function I put up there. That's the key to this. All right, now the next part, what is the probability is x within 2% true mean? We need the PDF of x to answer the question. Now, I put that is the density function of x bar up there. And if he wants to know what chances are you within 2%, so if you have that density function, you go to the lower limit, upper limit, and find the area between that. This class of questions, you want to know how confident you are in the calculation you made of the estimate or of the variance of the estimate. You have to create these variables, and this is what we were doing before. Remember how before it was just the value of x minus the mean of x over the standard deviation. Now what happens, it's not the standard deviation sigma, it's sigma over square root of n, because remember, sigma squared over n is the variance of the mean. So that's why he has this. Now, I'm going to say this: if the number of samples is small, or if it is not Gaussian, then you have to use the student t distribution. So that z, does this at least ring bells before? Remember, you took value minus mean over standard deviation, gave you the value you looked up. But you got to put in your table, didn't you put lower limit, upper limit, mean, and standard deviation and gave it to you in that calculator? The only thing you do is same as you did before. Here would be the value x, so that would be the limits. You're going to have 2 limits, upper limit, lower limit. That would be these values of x. So for this one, it would be 10.2, 9.8. Upper, lower. Then you put in the mean, 10. Now, where you normally put in the standard deviation, now, if it's a small number of samples, if it's a large number, you use sigma over square root of n. If it's a small, it's the actual calculated variance, square root of that, divided by square root of n. So you all remember the sample mean of a Gaussian is just, it is the actual, the mean value. The variance is sigma squared over n, assuming n is large, and that's important, or x or Gaussian. The normalized sample mean is also Gaussian. This is the normalized sample mean. Here we have sigma. We're using sigma because we either have a large number of samples, and he makes a statement n greater than 30 for this, or x of I are from a Gaussian distribution. Either one of those 2, you can use this. Otherwise, you got to use student t. What if the sample size is large and sigma squared is unknown? The only thing, if the sample size is large, but we don't know the sigma squared, now we replace sigma squared by s tilde or square root of n. So if s tilde of the square of that, say s tilde squared, if that is the variance of the samples, you take that and divide by square root of n, and you replace the actual value of sigma with that. This is the value if n is large or it's Gaussian. The standard deviation that you would use in your calculator would be sigma over square root of n, if you know the standard deviation of the actual population. Here's what happens if n is large and sigma squared is unknown. He gives you an example. You've got 100 bipolar transistors, large sample, it's over 30. He said we want the mean value, okay. True mean value is, see, this is for a sample. I think this is stated. We want the value of current data. Beta, it should be beta is the true mean value, and the variance, well, he does it backwards, so then he's using this as the true mean value, it's 120, and this is the variance of the samples, 25 amps. The range that you want, what is the probability that the mean is between 119 and 121? Well, that's straightforward. This is just a probability there. But then when you use your calculator, now, normally, what I do, I use the Q function. Take 119 minus 120, because it says that's the mean. This should not have a hat there. It should just be beta bar right here. So 119 minus 120 is just going to be minus 1, and this is going to be plus 1 here. Now down here, you've got 100 bipolar transistors. They give you a sigma of 25. So if you take 25 divided by 100, you get 1/4. Now take the square root and get 1/2. That's where this comes in. The standard deviation is now going to be the value of this s tilde squared divided by n, or 100 square root of that. And he puts this thing like probability from -2 to 2. When you do all this, because that's 1 over 0.5 is 2. -2 to +2. And he goes down and says 95% chance. Make sure you can do this on your calculators and know how to do it before you go into the problems. I got all the problems, but what do you do when the sample size is, what do you do when the sample mean, or the sample size is small in sigmas? I know that's where you use this Guinness thing. They're going to say, see this down here, V? It's the degrees of freedom. That V is the number of samples, n minus 1. If you have 9 samples, V would be 8. The rest of it is just like looking up a table for either the Q function. And here's the thing where he has them all down there. Now, here's some things I'm going to give you. Go through this stuff. He does a great job.